Hey everyone, and welcome to this explainer. Today we're diving deep into what I think is one of the most fascinating and honestly kind of counterintuitive parts of physics. We're talking about parallel circuits. If you've ever, stared at the wiring in your house or just wondered how all your electronics manage to run flawlessly at the exact same time without blowing a fuse, well, you're absolutely in the right place. Let's unravel this whole mystery together. So, let's kick things off with a bit of a brain teaser, a paradox, really. Because in pretty much every other area of life, right, adding an obstacle slows things down. You throw a big rock in a stream, the water slows down. You put hurdles on a track, the runner takes longer. Makes sense. But in a very specific type of electrical setup, adding more obstacles, which we call resistors, literally causes the total flow of electricity to speed up and the overall resistance actually drops. I mean, no way, right? How is it physically and mathematically possible that adding resistance pathways lowers the total resistance? That's the big puzzle we're going to solve today. Here's our quick roadmap for today's explainer. 1. The parallel circuit puzzle. 2. The tollway analogy for resistance. 3. Water pipes and current. 4. Voltage drops across branches. And 5. The math of equivalent resistance. Let's jump right into section 1, the parallel circuit puzzle. At its core, a parallel circuit is all about options. It's a circuit where the electrical devices are set up in their own completely separate branches. Think of a single road that suddenly splits off into multiple different paths. That exact splitting point, we call that a node. And the really cool part here is the idea of choice. When a flowing electric charge hits one of these branching nodes, it actually has to make a choice about which path it's going to take to get back to the battery. Every single charge making its way through the circuit will pass through just one resistor in one specific branch. It doesn't travel through all of them. It just picks one and goes. Moving on to section 2, the tollway analogy for resistance. Okay, picture a super busy highway. A toll booth is basically an obstacle, right? It forces cars to slow down, maybe stop entirely. That's our resistor. Now, if you have a massive highway but only one single toll booth, well, you've got high resistance and a massive traffic jam. But imagine we decide to build 3 more toll booths right next to the first one. Yes, technically, we've physically added more obstacles to our highway, but what actually happens to the traffic? It flows way faster. By adding more toll booths in parallel, we've opened up brand new separate pathways for those cars to get through, and this perfectly mirrors our electrical circuit. Even though we're adding components that resist the flow, putting them in parallel branches gives the charge additional paths to take. This brings down the overall resistance of the entire system, letting the total current surge. That brings us to section 3, water pipes and current. There's a really common misconception out there that electric charge somehow gets used up when it powers a light bulb or a gadget, but that's just not true. The rate that charge flows through a circuit is what we call current, and that charge definitely doesn't just vanish into thin air. A great way to think about it is water flowing through pipes. The rate that water flows into a branching pipe junction, our node, has to be exactly equal to the sum of the flow rates in all the separate pipes coming out of it. Electricity follows that exact same rule. The charge just divides itself into those separate branches. Let's actually visualize this step by step. First off, imagine water rushing into a main pipe at a pretty high flow rate, let's say 6 gallons per minute. Second, that rushing water hits a node and splits into 2 smaller separate branches. So maybe 2 gallons go down branch 1 and the other 4 gallons go down branch 2. The flow has divided, yeah, but not a single drop of water is lost. Finally, those 2 branches merge back into a single main pipe at the end, and the flow goes right back to that total of 6 gallons per minute. The big takeaway here is that in a parallel circuit, the total current flowing outside the branches is mathematically equal to the sum of the currents flowing inside the individual branches. The overall current is essentially exactly the same. It just temporarily splits into different lanes for a bit. Section 4. Voltage drops across branches. Let's focus on a specific number for a second, 12 volts. To really wrap your head around voltage in a parallel setup, think about a ski lift. A 12-volt battery is basically like a lift carrying skiers all the way to the top of a 12-volt mountain. Now remember earlier when we said a charge only ever takes one path? Once our skier reaches the very top, they make a choice and they take exactly one trail down. But regardless of which parallel branch or ski trail they pick, they have to drop that entire 12 volts of elevation to get back to the bottom. They spend their entire energy boost going down that one single path. And that whole ski lift idea brilliantly explains the mathematical rule for parallel circuits. The total voltage of the battery is perfectly equal to the voltage drop across branch 1, which is exactly equal to the voltage drop across branch 2, and so on. Now, unlike current, which splits up and divides among the different paths, voltage stays totally constant across every single parallel branch. Whatever voltage elevation a charge gets from the battery is completely spent as it travels down its single chosen path. Finally, we arrive at Section 5, the math of equivalent resistance. Before we dive into the actual formulas, let's quickly define equivalent resistance, or REQ for short. Equivalent resistance is basically just a mental shortcut for simplifying a super complex circuit. It's the exact amount of resistance a single hypothetical resistor would need to have to equal the combined overall effect of all the separate resistors sitting in those parallel branches. Basically, it's asking, hey, if I wanted to replace all these tiny obstacles with just one giant obstacle, how big would it need to be to make the battery do the exact same amount of work? So here's how we actually calculate it, and I'll walk you through this nice and slow. Step 1, we use a reciprocal formula. It goes like this. 1 over the equivalent resistance equals 1 over the resistance of branch 1 plus 1 over the resistance of branch 2, and you just keep going for however many branches you have. Step 2, you plug the actual ohms of your individual resistors right into the bottom of those fractions. And finally, step 3, you add those fractions all together, and then, now this is the absolutely crucial part, don't forget this, you invert that final fraction to solve for the equivalent resistance in ohms. And honestly, because we're adding these fractions, the math itself perfectly proves that wild paradox we talked about at the beginning. Let's actually see this math in action with a couple of test cases. So in case 1, we've got 3 resistors running in parallel, and they each have 12 ohms of resistance. When you run them through our fraction formula, the total equivalent resistance drops all the way down to just 4 ohms. Pretty cool, right? In case 2, we mix it up with resistors of 5, 7, and 12 ohms. Add up those reciprocals, invert the final fraction, and your total equivalent resistance is a mere 2.3 ohms. These results highlight literally the most amazing fact about parallel circuits. The total equivalent resistance is always, always less than the smallest individual branch resistor in the whole circuit. Because you're offering multiple pathways, the entire circuit becomes vastly easier for the electricity to flow through than any one single branch on its own. All of this brings us to a beautifully simple and honestly super relatable truth about physics. Charge, a lot like people, always chooses the path of least resistance. Ohm's law tells us that current and resistance are inversely related. So because the voltage drop across all those parallel branches is completely identical, the specific branch that has the lowest resistance will always, for sure, experience the highest flow of electrical current. The electricity just naturally surges down the absolute easiest possible path. Well, that brings us to the end of our explainer, but I want to leave you with something to think about today. Take a look around your home. The lights, your TV, the fridge, they're all wired in parallel. It's exactly why you can switch off a lamp without plunging your entire living room into total darkness, or why turning on the microwave doesn't magically slow down the ceiling fan. But if electric charge naturally seeks the path of least resistance, how do you think this physical law dictates the way electrical engineers safely design those hidden circuits running inside your own walls? I mean, what happens when way too many easy paths are opened up all at once? I'll let you ponder how the magic of multiple pathways powers our entire modern world. Thanks so much for joining me on this deep dive, and keep asking questions about the world around you.